Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. So today we are going to discuss computer arithmetic, addition and subtraction. So in computer arithmetic, we are performing different arithmetic operations. So mainly we have four arithmetic operations are there: addition, subtraction, multiplication, and division. So in this lecture, we are going to see how we can perform addition and subtraction on the signed numbers. So arithmetic instructions in digital computers manipulate data to produce results necessary for solution of computational problems. So these instructions perform arithmetic calculations and are responsible for the bulk of activity involved in processing data in computer. And here we are discussing four types of basic arithmetic operations, that are addition, subtraction, multiplication, and division. So from these four basic operations, it is possible to formulate other arithmetic functions and solve the scientific problems by means of numerical analysis methods. So using these four basic operations, we are going to formulate the other arithmetic operations, and that can be used to solve the scientific problems by means of numerical analysis methods. Okay. So here we are performing these arithmetic operations on the signed numbers. Okay. So the signed numbers we can represent in two ways. One is the signed magnitude form and the signed and the complemented form. Okay. First one is a signed magnitude form, and second one is in complemented form. So these are the two types. So in signed magnitude form, so we can represent. So the syntax is so we have a signed bit and the actual binary number. So this is a syntax for the signed magnitude form. And coming to the complemented form, so we can represent the signed numbers in the complemented form. That means we have two types of complements are there, that are ones complement and the twos complement. So using ones complement and twos complement, we can represent the signed numbers. So we develop the various arithmetic algorithms and show the procedure for implementing them with the digital hardware. We consider the addition, subtraction, multiplication, and the division for the following types of the data. So already we have seen we have a four basic arithmetic operations are there. So we are performing all these arithmetic operations on two types of data. So the first one is a fixed point binary data. Fixed point binary data in signed magnitude representation. Second one, fixed point binary data in signed twos complement representation. So we have two types of representation. One is a signed magnitude, and next one is a signed twos complemented form. So there are three ways to represent the negative numbers, negative fixed point binary numbers. First one is a signed magnitude, signed ones complement, and signed twos complement form. So the most computers, it will use signed twos complement representation when performing arithmetic operations with integers. Okay. So when the computers working with integers, it will use a signed twos complement representation, because always we represent these integers in signed twos complement representation. And for floating point operations, most computers use signed magnitude representation for mantissa, because here the floating point floating point numbers we can represent it using the mantissa and exponents. So in order to represent the mantissa, we are using a signed magnitude representation, and for exponents we are using integers. So in this section, So we develop the addition and subtraction algorithms for data represented in signed magnitude and signed two's complement forms. So let's see how we can perform the addition and subtraction using signed magnitude data. So the representation of numbers in signed magnitude is familiar because it is used in everyday arithmetic calculations. Because the signed magnitude is familiar because in our daily life we are using the signed magnitude numbers. So that's why everyone is familiar with these calculations. And the procedure for adding and subtracting of any two numbers, which is similar to the paper and pencil, is simple and straightforward. Okay, so a review of this procedure will be helpful for deriving the hardware algorithm. So why we are reviewing this paper and pencil procedure? Because that is very simple to implement this hardware algorithm, and we designate the magnitude of the two numbers a and b. So here, in order to perform this addition and subtraction in signed magnitude numbers, so we are considering two registers. One is the register A and another register is the register B. So between the two numbers or between the two registers, we are performing this addition and subtraction. So when the signed numbers are added or subtracted, we find that there are 8 different conditions to consider. So when you are performing this, when we are performing addition or subtraction something between the two registers, 8 different conditions we have to consider. So depending upon the sign of the numbers and operation they perform. Okay, so based on the sign of the numbers and the operation they perform, these total 8 different conditions to be considered. So let's see. So these conditions are listed in the first column of the table. So here we are mentioning in the first column, so we are specifying the condition, and in the next one add addition, and this is for addition, and this is a subtraction. So we are performing addition and subtraction. Okay, so see here. So here already we have seen. So in order to perform this addition and subtraction, we have considered two registers. One is A and another one is B. So these are the two registers. Okay, so based on the sign and based on the operation they perform, so total the operations are 8 different combinations we need to consider. So let's see. So first one is plus A plus B. So this one. Okay. So here all the different registers we have specified with different signs. So here what we are doing. So in addition, so the registers with the same sign. So the registers with the same sign. So what are the registers with the same sign? So see here. So this is the first one. So plus A plus B. Because if you see the sign of the number, so sign of the register. So sign of the register both are positive. Okay. So that is the first case. Next one, this one. Fourth one, minus A plus minus B. That means the sign of the register or the sign of the numbers are same, because here it is a negative number, here it is also a negative number. Their signs are same. So plus means it is a positive number, minus means it is a negative number. So here in the first case both are positive numbers, in the second case both are negative numbers. And the last case, so the last case is minus A minus B. So here signs are same. Okay. So see here. So here add magnitude. So when the signs of the two numbers are same or similar, then we have to add the magnitudes and take the sign of the first number. So if you represent the first case, here the sign of the both numbers are same. That means both numbers are positive only. So I am adding the magnitudes. What is the magnitude of the first one? A. A is the magnitude and plus is the sign of the number. B is the magnitude. So what are the I am adding their magnitudes. So A plus B, and I am taking the sign of the first register plus. Okay. So similarly this one. So both here in this case both the numbers are having the same sign. That means minus A and minus B. So I am adding their magnitudes A plus B. I am taking the sign of the first register minus. Similarly here this one. So plus A plus B. I am adding the magnitudes and taking the sign of the first register. And next one, last this one. So here in the last case also the sign of the both the numbers are same, minus A minus B. So I am adding their magnitudes A plus B and taking the sign of the first number minus. So this is a addition. So in this way we can perform the addition. And we are performing subtraction. So when we are performing subtraction, when the two registers are having different signs, or when two numbers are having different signs. What are the different signs? That means plus and minus, minus and plus. When the signs are different, we are performing subtraction. Okay, when signs are different, we are performing subtraction. Similarly, when the signs are same, that means plus and plus, minus and minus. We are when the signs are same, we are performing addition. Okay, so see here. So these are the two. So for this, the signs are different. This is plus A and this is a minus B. Signs are different. Second one, minus A plus B. So the signs are different. So when signs are different, we are performing subtraction. Okay. So subtraction, that means here we have to subtract the magnitudes. When you are performing subtraction, so total three cases will exit. So that are A greater than B, A less than B, A equal to B. Okay, so these are the three different cases we need to consider in the subtraction. So let's see, first one, A greater than B, A greater than B. So A greater than B. So what will happen? Subtract magnitudes. So when A is here, the condition is A is greater than B. That means the contents of register A is greater than the contents of the B register. So in that case, we have to subtract their magnitudes. So that's why A minus B. And we have to take the sign of the first number. That is nothing but A register. What is the sign of the A register? A. So that's why here the sign is plus. Okay. So this one. Next one, minus A plus B. So for this case also, the signs are different. The first number is negative number and the second number is a positive number. So signs are different. So if signs are different, what I have to do? I have to subtract their magnitudes and I have to take the sign of the first larger number. Okay, what is a larger number? A. A is greater here, greater number. So that's why I have took the sign of the larger number and I have subtracted their magnitudes. Okay. And next one, where the signs are different are there? So this case. So see here plus A minus B. So their signs are different. So a minus b, and what is the sign of the larger number? Plus. So plus, and here this one. So first number is negative number, second number is a positive number. So I have to subtract their magnitudes, a minus b, and I have to take the sign of the first number, minus a minus b. So this is a first case in the subtraction. When a is less than b, when a is less than b, when a is less than b. So that means here the b is greater. So in this case also we have to subtract the magnitudes, but we have to take the complemented sign of the larger number. So let's consider one case. So this one. So see here. So plus a minus b. So what I have to subtract the magnitudes, a minus b. I have to subtract their magnitudes. So here what is there? B is larger. So that's why b minus a. B is larger number. Okay. So b is larger number and a is a smaller. So that's why we are subtracting a from b. Okay. And here what is a, see, we have to take the complemented sign of the first number. So what is the sign of the first number? Positive. So what is the complement? It's complemented negative. So positive means it is a 0. Positive means 0. If it is complemented 1, 1 represents negative number. Minus 1 represents a negative. Similarly, next one, minus a plus b. So here also b minus a. So here what is the sign of the first number? Minus. So what is its complemented value? Plus. So this is a second case. Second one. Third one, a is equal to b. So suppose if the value of both the registers are same. Here this is the condition. So when you subtract any two numbers, we have to get a positive 0. We should not get the negative 0 because the negative 0 is not existed. So that's why we have to get the positive 0. So that's why we are subtracting when a minus b. If the a and b values are same, then you will get the 0. And here plus is there. So that means plus 0. So these are all the zeros. Okay, so this is a performing addition and subtraction. So when the signs are same, it performs addition, and when signs are different, it performs subtraction. So now we are moving to the algorithm for addition and subtraction are derived from the table and can be stated as follow. So based on this table, so we are going to develop an algorithm in order to perform the addition and subtraction on the signed numbers and two's complement numbers. So first one, addition algorithm, addition or subtraction algorithm. So when signs of a and b are identical, add the magnitude and attach the sign of a to the result. So this is we did before. So when the signs of the a and b are identical, what we are doing? We are adding their magnitudes and taking the sign of the a number, larger number. We are taking the sign of the a to the result. And second one, when the signs of a and b are different, when the signs of a and b are different. So when the signs of two numbers are different, so here we have to consider three cases. The first one is a greater than or b. First case is a greater than b, and second one is a less than b, and third one is a is equal to b. So just before we have seen all these three different cases for the subtraction, and the two algorithms are similar except for sign comparison. The procedure to be followed for identical signs in the addition algorithm is the same for the different signs in the subtraction algorithm, and vice versa. So see here. So here what we are doing here. So when the signs are same, we are performing addition. When signs are different, we are performing subtraction. Okay. So when signs are same, we are performing addition. When signs are different, we are performing a subtraction. Similarly, see here, when the signs are same, when signs are same for the negative numbers, even it results a addition. So coming to the hardware implementation, so to implement the two arithmetic operations like addition and subtraction with the hardware, we have to consider two registers, that are register A and register B, and let AS and BS. So AS is a sign of the A register. So sign of the register A register will be stored in the AS register. So AS and BS are these are the one bit. These are the flip flops. So flip flop is nothing but in that flip flop we can store either logic 0 or logic 1. Only one bit we can store at a time. Okay. So the sign of the A register we are storing in AS, and the sign of the B register we are storing in BS register. So the results are transferred to A and AS. So finally, after adding, the result automatically will be stored in the register A, and its sign will be stored in the AS. So A and AS together form an accumulator. So that both A and AS together, it will form a accumulator. So this is a hardware for signed magnitude, addition and subtraction. So already we know we have two registers, A register, B register, and two flip-flops to store their signs, AS, and this is a BS. So AS means sign of A register, BS means sign of B register. Okay, and then we have a parallel adder. Then we have a parallel adder and one extended flip-flop E, complementer, and one overflow flop, arithmetic adder overflow, AVF, adder overflow. So these are the different hardware we are using. And here mode control. So one mode control input is there that we are applying to complementer and the parallel adder input carry. So this mode control bit we have applied to the input of the parallel adder as input carry. And this is a load symbol, load sum. So here let's say A is equal to 5, B is equal to 4. So these are the two different registers, A and B. And let us assume both numbers are positive. Both numbers are positive number. So positive number is nothing but here in this AS we will store 0, here also 0. And A and B register. So let us assume some 4-bit registers are there. 5, 0, 1, 0, 1. 4, 0, 1, 0, 0. So in A register we have stored 0, 1, 0, 1. Here we have stored 0, 1, 0, 0. So now we are performing addition. So for addition, the mode control should be 0. The mode control should be 0. So if mode control is equal to 0, then this accumulator register data, it will be added with the contents of the B register. So the B register here, it directly given to the parallel adder without performing complementing. So that means B register data, it is added with the A register data. So after that, it is added. It will be added in the parallel adder. After that, it will generate any carry. If there is any carry, that will be stored in the extended flip-flop. Otherwise, the result will be there. So after adding, what will be there? So input carry is the 0. So adder. So 0, 1 plus 0, 1. 0 plus 0, 0. 1 plus 1, 1. Adder. So 0, 1. So here 0. So here adder, parallel adder. Okay. Just a minute. So see here. So one. So parallel adder. So you will get here. So 1 plus 1, 1, 0, 1, 0, 1. So total you will get 9. So when you add this 5 with 4, so 5 plus 4, you will get the 9. So here we didn't get any carry because there is no carry generated. So that's why in this extended flip-flop, we will store 0, and in the parallel output, it will store 1, 0, 0, 1. Okay. After whenever the result is generated, so this 0, whenever the operation is completed, the value which is stored in the extended flip-flop will be moved to the adder overflow. So this is for addition. And similarly, when we wish to perform the subtraction, so in order to perform the subtraction, the mode control input should be logic 1. So here it is 1. So whenever if the mode control input is given 1, here logic 1 is applied to the complementer, and the input carry also 1 here. Input carry also 1. So what will you see here? So here it is a complementer. So complementer. So this whatever the data present in the B register, it will be complemented. Then it will be given to the parallel register, parallel adder. So here what will happen? So after if you perform a ones complement to the B register, you will get ones complement. Okay, that means B bar. What is B bar? B bar is the ones complement of the B register. Next, in the parallel adder, 1 adding here. So 1 adding here. Input carry is 1. Okay. And the contents of A register. The contents of A register. A. So all these 3 gets added. A plus B bar plus 1. So it is equal to A minus B. Because we don't have negative numbers directly. So negative numbers always, it will be represented in the 2's complemented form. So this B bar plus 1. So B bar plus 1, it is equal to 2's complement. It is equal to 2's complemented form. So that is equal to A minus B. So this is a operation. So in this way, we will perform the subtraction. Okay. So hardware algorithm. The two signs A and B are compared by exclusive OR gate. Okay. So how we can perform, how we can implement the algorithm. Okay. Hardware algorithm. So this is a hardware implementation. So using this, we are going to implement the algorithm for the addition and subtraction. So the two signs A and B are compared by exclusive OR gate. So already we know. So we have two numbers. We have A and B. So these are the two registers to store two different numbers. And here the sign of the A register is AS and the sign of the B register is BS. So this is a single bit. AS is a single bit. BS also single bit. So in between them we are performing exclusive OR operation. Exclusive OR operation. So based on that, we are deciding whether the number is positive or negative. Okay. So if the output of the gate is 0, their signs are identical. So if the output is equal to 0, their signs are identical. Identical is nothing but it is a same. The signs are same. If the signs are different, if the output of the gate is 1, then the signs are different. It is a logic we are using to implement the hardware algorithm. So first we have to decide whether the signs are same or different. So using this logic, we are going to decide whether the signs are same or different. So for an add operation, identical sign dictates that the magnitudes be added. For subtraction operation, different signs indicate that the magnitudes will be added. Okay. So the magnitudes are added with the micro operation a plus b. A plus b. So if their signs are identical, then we are going to add their magnitudes. So a plus b. Then the result will be stored in the EA, extended accumulator. So A is the accumulator, and the sign of the accumulator will be stored in the this E, extended accumulator. So E is a sign of the result. So the carry in A after addition constitutes an overflow if it is equal to 1, and the value of E is transferred into the add overflow flip-flop AVF. So this is a hardware algorithm for addition and subtraction. So here using this flow algorithm, we are implementing addition operation and subtraction operation. So augment in A, added in B. So in order to perform addition and subtraction, we require two registers. One is register A and register B. Okay. So we are adding A plus B. So that means the contents of B register we are adding with the contents of the A register. So this B register is called add end. Add end. So this A register is called augend. Augend. So the bits in B register is called addend bits. The bits in A register are called augend bits. So these two registers we are going to add. Similarly, the subtraction. Okay. So in addition, how we are deciding whether the signs are same or different using XOR operation. Using XOR operation. So what is XOR operation? If their signs are same, then output is 0, and if the signs are different, the outputs are logic 1. So here the signs are same, so output is logic 0, and here the signs are different, so output is logic 1. Okay. So see here. So if their signs are same, so if the signs are same, the result is 0. The output of the XOR logic gate is 0. So here AS XOR BS. So AS XOR BS. That means in AS we will store the sign of the A register, and in BS we will store the sign of the B register. So between these two sign bits we are performing this XOR operation. Suppose if you have a plus A and plus B. So what is the sign of both the numbers? Both numbers are positive only. So both numbers are positive means the sign of both the registers. In AS we will store 0, BS also 0. So 0, 0. So there's 0, 0. That means output is 0. So output is 0 because the signs are same. So if the signs are same, what we are doing? We are adding their magnitudes. So that's why A plus B. What is A? Magnitude of A. What is B? Magnitude of B. So their magnitudes we are adding, and the result will be stored in the EA, extended accumulator. Okay. Next, if any, after performing the operation, after adding magnitude, if any extra overflow occurred, that will be copied to the AVF. Then that operation will be performed. So that particular AND operation will be finished. Next, suppose if the different signs are there, what will happen? If the signs are not same, if the signs are not same, then we are performing subtraction. Suppose you consider a another number, that is see here. plus A minus B. So in between these two we are performing the addition. So if the signs are different, what will happen? If the signs are different, then we have to add their magnitudes. Okay. So if the signs are different, then we are performing subtraction. Okay. So see here. So here the output of the XOR gate is 1 because the signs are different. So this is the case. So output is logic 1. So output is logic 1. So when the signs are different, we are performing a subtraction. How we can perform subtraction? We are performing, first we are taking 2's complement of B register and we are adding 1. Okay, so that you will get the B bar plus 1. So B bar plus 1, so that is equal to negative number, negative minus B, that is equal to minus B. So this minus B content we are adding to the A, so that is equal to A minus B. So here A plus, so here A plus B bar plus 1. So that means what we are performing here, we are performing A minus B. That means we are performing subtraction operation. Okay, and here when we are performing subtraction operation, so here we will not get any overflow here, AVF 0, because in subtraction we are not getting any overflow. So that's why the 0 will be loaded into the AVF. Next, E, we are checking the E is equal to 1. So when E will be 1, when extended flip-flop, E will be 1 if A is greater than or equal to B. In this case only we will get the E is equal to 1. So in subtraction already we have seen 3 cases: A less than B, A greater than B, A equal to B. So E is equal to 1 when A greater than or is equal to B. So here, so again here we are checking A, register. So is A equal to 0 or not 0? Okay, so if A is equal to so if the A is equal to B, so what will happen? If both numbers are same, then the result will be 0. So that's why 0. So here we are checking the register A. If A is equal to B, if the both registers having same sign, then what will happen? Then you will get the result 0. Result 0 means so result 0. That means when you subtract, when you after performing subtraction, we have to get the positive 0 only. So just before also we have seen we have to get to only the positive 0. We don't have negative 0. So that's why we are loading 0 into the sign of the A register. So that means the result, the accumulator register, it contains a positive 0. Okay. Next, so when A greater than B, so first case is, we have seen here. We have seen 2 cases here: A greater than B, A equal to B. So A equal to B we have seen. So this is A greater than B. So when A greater than B, the result of the accumulator result will not contain 0. So that means after performing subtraction, A minus B, so A is a larger value. That means you should not get 0 value because you will get some finite value here. So that's why here not equal to 0. And the result will be stored in the accumulator and AS. So this is one. Similarly, if A less than B, so that means you are performing B minus A. We are performing B minus A operation. So that's why A bar will be loaded into the A. A bar will be loaded into the A. Okay. Here A less than B. So A bar will be loaded into A. So A bar means it is a complemented. Next, A plus B. So here we are performing B minus A. So how we can perform B minus A? B plus minus A. So how we are representing negative numbers? The negative numbers are represented in 2's complement, signed 2's complement form. So what is the 2's complement form of this minus A? First we have to find the 1's complement. 1's complement of A is A bar. And how we can get the 2's complement? By adding 1 to the 1's complement. So this is 1's complement. So now I am adding 1 so that it will become a 2's complement. So this is equal to B minus A. So that's why first I performed 1's complement. 1's complement. So here I have performed 1's complement. After that here I have added plus 1 so that it will become a minus A. So this minus A I am adding with B. Next, see, AS bar will be loaded into the AS because when you perform this A less than B, that means we are performing B minus A. That means we have to complement the sign of the A register also. That's why AS bar will be loaded into the AS. Okay, so this is a addition. And coming to the subtraction. So in subtraction, when the signs are when the signs are different. So these are the different. When signs are different, what will happen? We will perform addition. When signs are same, we will perform addition. Okay. See, when signs are same, see this case. When signs are same, it performs subtraction. So subtraction, it will perform subtraction. When signs are different, it performs addition. So it will perform the addition here. Okay. So see here. In addition operation, when signs are same, it performs addition operation. When signs are different, it performs subtraction. Okay, clear? Coming to the subtraction. So in subtraction, when the signs are same, we will perform subtraction. When signs are different, we will perform addition. Okay, so this is a hardware algorithm to perform the addition and subtraction. So till now we have seen the addition and subtraction for the signed magnitude number. Now we are going to see for addition and subtraction of signed 2's complemented form. So in signed 2's complemented representation, the leftmost bit represents the sign. If the sign bit is equal to 1, entire number is represented in a 2's complemented form. So addition. So the sign bit is treated as the other bits of the number. Carry out of the sign bit is discarded. So in 2's complement addition, if there is any carry is there generated, that carry can be discarded. And coming to the subtraction, it consists of first taking 2's complement of the subtrahend and then adding it to the bind. When two numbers of n digit are added, the sum occupies n plus 1 bits. Overflow occurs, which is detected by applying last two carries out of the adding to XOR gate. The overflow occurs only if output of the gate is 1. So see here. So this is a hardware implementation of for the adder and subtraction of signed 2's complemented data. So see here. So this is AC register and this is a BR register, accumulator register, B register, and complementer and adder. So here it performs the signed 2's complemented operation. So this is a overflow. And coming to the hardware algorithm, in addition. So here addition, we are adding BR register data to the accumulator. So that means the contents of accumulator is added with the contents of the BR register, and the result automatically will be stored in the accumulator. And if there is any overflow occurred, then that will be stored in the V, and it will be finished. The addition operation will be completed. And coming to the subtraction. So for subtraction, the minute will be stored in AC, and the subtrahend will be stored in the BR register. And we are performing the subtraction. So here we are performing AC minus BR. So already we know the negative numbers are represented in the twos complemented form. So what is the ones complemented of BR register? BR bar. Then we are adding 1 to that register, so that this is equal to the twos complemented value. So this is the twos complemented. So this is equal to minus BR. Okay. Then we are adding it to the accumulator. So this is equal to AC minus BR. And overflow we are loading into the V. Then the operation will be ended. Okay. So this is a hardware algorithm for addition and subtraction of signed twos complemented data. So in this lecture, so we have seen the addition and subtraction for the signed magnitude numbers and signed twos complemented data. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.